In this lesson, we're going to compare metallic and covalent bonding. Instead of electrons being completely transferred like in ionic bonding, today we'll see what happens when electrons are either free to move throughout, as they are in metallic bonding, or shared between atoms, covalent bonding. By the end of this lesson, you should be able to distinguish between these two bonding types and correctly name covalent compounds using prefixes. So if we're going to start out with metallic bonds, so when two metals combine together, they form metallic bonds. Kind of makes sense. Because of the low ionization energy of the metals, the electrons are not transferred, they're not shared, they just kind of go into a pool around the metal centers. This electron C is due to the delocalization of the electrons, and they are surrounding the positive metal centers, the nuclei. So the core electrons are also going to be attached to the metal centers. And so in this diagram, we have a bunch of the metal centers, and we just kind of have this blue thing around it. It's supposed to represent a wire. This is not one of my better animations, but you can see when you pass a current through a wire, the electrons don't go straight through. They kind of wander around. And then the higher the temperature, the more wandering they're going to be doing because they bounce off of the metal centers, and it causes a lower drift velocity. At any rate, the properties when you have metallic bonding, you end up with the same characteristics as you had with metals. So the metals, or with metallic bonding, because the electrons are delocalized, the metal will be shiny. It responds to the electric field component of the incident light, causes it to reflect. They are malleable and ductile, so if you apply pressure to it, they just kind of squish out of the way. They're not brittle like the ionic solids were, and they are good conductors of heat and electricity. So alloys are mixtures of two or more metals. There are three types of alloys. The first one is, I think most places call it a combination alloy or a substitution alloy. I did my research when I was in graduate school on alloy nanoparticles, and we always called them solid solutions. And so in a solid solution, the placement of the different metal atoms that are mixed together is completely random. So in the case of this first one, which is 1/3 silver, 2/3 gold, if you just kind of pick an atom at random, 33% of the time it's going to be silver, and then the remaining part of the time it's going to be gold. Now it turns out that metals do not like to mix with each other very much, especially when you start talking about nanoparticles. The particles that I was trying to make in my graduate research were platinum-ruthenium nanoparticles, and if you gave them even just a little bit of thermal energy, all of the platinum would segregate to one spot and all of the ruthenium would go to another spot. They did not like being mixed together. So that would be an example of a heterogeneous alloy. It's not just nanoparticles that do this. One of the labs that I did when I was learning electron microscopy was we would use an electron microscope to generate X-rays coming out of some solder joints. So solder is a mixture of lead and tin and some bismuth and things like that. And the X-rays that are generated are characteristic of the elements generating them. And so we would tune it to, say, the lead part of the lead X-rays, and you'd see one part of the screen would light up because that's where all of the lead had segregated. And then you tune it to the tin part, and you'd have a different part of the screen light up. And so that was actually kind of interesting because it showed that even in the bulk phase, metals still really don't like to be uniformly mixed with each other. They tend to segregate. And then the last one isn't really a mixture of alloys, but it is a mixture of elements. They're not chemically bonded to each other. So this one is called an interstitial alloy. And so I'm sure you've heard of this before. An example is carbon-hardened steel. And so the reason why, and it's not bonded, so let me point at the picture. So the big gray spheres are the the iron atoms, and the smaller ones, the red spheres, are the carbon atoms. And so the carbon atoms fit very nicely into the spaces or the interstices between the iron atoms. And because they're there, it keeps the iron atoms from being able to kind of smoosh around. That's how the carbon bonds to it, hardens it. The carbon is not bonded, chemically bonded to the iron. It's just sitting there in its atomic form. So speaking of my graduate research, it was on making nanocomposite materials. And so the earliest example of a nanocomposite material that I could find was the Lycurgus cup. And it was made somewhere in the 4th century AD. And it had some unusual optical properties in that if you shined light directly on it, it would have this kind of, and it's the stuff behind the stuff that's on the surface. It would have this kind of icky green color. But if you shine light from behind it, you get this real pretty red color. So these dichroic properties, 2 colors, are due to the fact that there were an alloy of silver and gold present in the glass matrix. These particles were about 60 nanometers across, and the optical properties of these particles were such that they caused these different colors to appear with the light. So it's the silver component that caused it to look kind of greenish, and then it's the gold component that caused it to have that pretty red color. So mine was to make platinum ruthenium particles 1-to-1 on graphitic carbon. And so this picture down in the bottom right is an electron micrograph, transmission electron micrograph of my platinum ruthenium particles on the graphite. And so these dark blobs are the platinum ruthenium particles. They are more electron dense, so they block more of the electron beam, and that's why they look darker. And this squiggly lines you can kind of see in the background are from the separation between the planes of the graphite. This particle or this image was taken at Oak Ridge National Labs at about 1,000,000 times magnification. And it took forever to get this picture because the slightest little bit heating of the sample stage from the electron beam would cause it to drift. And so all day long it was like, oh, here come some particles, and by the time I managed to get everything focused, they had already drifted off screen. All right, let's go on to the next part. So covalent compounds. So because of the differences in ionization energy and electron affinities between nonmetals, it's very minimal. That means that they're not going to want to transfer electrons. They're going to share electrons. So remember last time we said that you can't call an ionically bonded solid a molecule because it's just a ratio of the cations to the anions. When you're talking about covalently bonded compounds, it is a molecule. And that's because they are separate, discrete little units. There is the octet rule, which says that in general, atoms are going to gain or lose electrons in order to have 8 electrons around them when they are all bonded together. So we're going to learn how to draw Lewis structures, which is just a 2-dimensional representation of how the things bond together. So each one of these little dots is a valence electron from either the oxygen or the hydrogen. Remember with oxygen, it has 2 pairs of electrons to begin with, and so these are actually called lone pairs. I prefer to use sticks to show the bonding pairs of electrons because getting all those dots and keeping track of all of them is a little confusing. So one of the things we're going to do is we're going to look at how to go from this flat 2-dimensional Lewis structure and figure out what it's going to look like in 3D. So water, not too exciting. You could have a ball and stick representation, which is probably the one you're most familiar with. There's also something called a space-filling representation, but we're probably going to focus more along on the ball and stick type of modeling. So as I said, when you have 2 nonmetals combining together, they're going to share electrons. And so one of the reasons why we spent so much time on drawing proper electron dot structures is pretty much whenever you have an unpaired electron on the electron knot structure, it's going to, on a nonmetal, it's going to pair up with another unpaired electron on another atom to make a covalent bond. So here we have hydrogen, it has one unpaired electron, the oxygen has two unpaired electrons, and then the hydrogen on the other side will pair up with that unpaired electron. And so we do that. And now they are shared in between the covalent bond, so we would probably want to draw that as a stick. It is important to remember that these electrons are not stationary. They are moving. They can be polarized. They will spend more time around the oxygen, and then they go back down towards the hydrogen. It's because the electrons are localized between the nuclei that molecular compounds don't stick together as tightly as if they had the permanent positive and negative charges, like you see in the ionically bonded solids. This causes molecular compounds to have low boiling points and to be soft solids or liquids. Remember, ionically bonded compounds had high boiling points and they were brittle solids. There we go. All right, so nomenclature. One of the things that's really nice about covalently bonded compounds is we don't have to do the swap and drop thing or anything else like that. You're just going to tell the listener how many you have of each type of atom when you are naming the compounds from their formulas. And so it's kind of like what you would do in geometry. So 1 is mono, 2 is di, 3 is tri. The one that gives people the most trouble is tetra. Tetra is 4. Just think Tetris with the little boxes, the cubes and stuff like that. They have 4 sides. Tetra is 4. And then it kind of continues on. There's more past deca, but I tend to not go anything bigger than deca. So let's just do some practice. So here we have CO2. We have 1 carbon, 2 oxygens. One of the oddities for the rules on how to name things is that if you only have one of the first element, you don't say mono. The only time you use mono is when it's for the second element. So this is the very familiar carbon dioxide. Go on to the next one. So we have 2 nitrogens and 4 oxygens. So this is going to be dinitrogen, so 2 nitrogens and 4 oxygens, tetroxide. You could also write it as tetraoxide. As far as I know, there's no fixed rule as far as whether it's tetroxide or tetraoxide. SF6, kind of have your little list out and ask yourself what that would be. So that would be sulfur hexafluoride. Notice that the second element, just like with ionic compounds, you chop off the ending and change it to IDE. So you would not say sulfur hexafluorine. It has to be sulfur hexafluoride so that we know that they're all bonded together. Then we have PCl5, which would be phosphorus pentachloride. SO3, sulfur trioxide. NO, a very negative molecule, is nitrogen monoxide. Notice we don't say mono for the first one, but we do say it for the second one. And then the last one for this part would be XeF4, it would be xenon tetrafluoride. This is one of the compounds that xenon and fluorine will make. So now let's go the other way. This is probably easier. So we're going to say sulfur dioxide. So that tells us we have 1 sulfur and 2 oxygens. So SO2. Diphosphorus tetroxide. So that would be P2O4. Notice we do not simplify this because this is a single discrete particle, a molecule, that has 2 phosphorus and 4 oxygens in every single one. And then we have krypton tetrafluoride, so that would be KrF4. Carbon monoxide, so it's got that mono on there, so that tells you it only have 1 oxygen. Dinitrogen trioxide, so N2O3. And then boron tribromide, BBr3. This one got included because there are a lot of elements that start with the capital letter B. Make sure you're using the right one because B by itself is boron, Br is bromine, Bi is bismuth. You got to make sure you're using the right symbol. And in the last example, sulfur tetroxide, S2O4. So again, we would not simplify that. Some mixed practice. This is actually just some rules to keep in mind because we're going to getting ready to go back and forth between ionic and covalent. And so ionic, the general rules are you have a metal plus a nonmetal. So as soon as you see a metal, you know it's ionic. Or if you see that you have polyatomic ions present, it's going to tell you that it is an ionic compound. So the cation goes first. And if you have a transition metal, you got to say what the oxidation number is, also for lead and tin. For both of them, you're going to change the ending of the second element to IDE. Polyatomic ions get to keep their names, so you wouldn't change it to IDE in that case. And you do not use prefixes with ionic compounds. Once students learn about the prefixes, that's the only thing they want to use. So make sure, if you remember, if you're talking about an ionic compound, do not use prefixes. So covalent. So you have no metals or ions present. So just like before, the first element gets to keep its name. You don't use mono on the first element if there's only one of them. The only time you use mono is when it's for the second one. Change the ending of the second element to IDE. And this is where you are allowed to use prefixes. All right, so we got some practice. Hopefully I left myself enough space. So the first one, we say Ca2C. All right, so Ca is calcium. That is a metal. It's over on the left-hand side of the table. It's not a transition metal. So we say, all right, metal, ionic, no prefixes. So it is just going to be calcium, and then you chop off the ending of carbon and make it IDE, so it becomes carbide. And we have next one. All right, so nickel is a metal, so we're going to use the ionic rules. Nickel is also a transition metal. So we have to figure out, oh dear, I lost a suffix. There's supposed to be a 2 there. So we have acetate. It's one of the polyatomic ions. We have 2 of them. So that has a total charge of -2. So that would be nickel with a +2 charge. So this one is nickel, Roman numeral 2, acetate. On to the next one, P2O5. So both phosphorus and oxygen are nonmetals. So that means we get to use the prefixes. So diphosphorus. Pentoxide, because penta is 5. Then we got SF4. Sulfur and fluorine are both nonmetals, so we get to use the prefixes again. So we have sulfur. We don't use mono because it's the first one. And we have 4 fluorines, so tetrafluoride. And then we got this guy. So sulfur is -2. Copper is a transition metal, so we have to figure out the oxidation number. Sulfur is -2. So the total positive charge has to be +2, but we have 2 coppers, so that means each copper is +1. So it'd be copper, Roman numeral 1, sulfide. All right, now let's go the other way. So potassium phosphate. All right, I see that I have the ATE in there. That is a polyatomic ion, so I know I have to do the swap and drop. So I say, all right, well, potassium is in group 1, so it's +1. I look up phosphate. It's PO4, the -3. So I swap and drop the top numbers, and the formula ends up being K3PO4. Then we have silver sulfate. Sulfate is a polyatomic ion, and hopefully you know that silver is a metal. So we say, all right, well, silver always has a charge of +1. Sulfate is SO4 with a -2 charge. So we swap and drop the top numbers, and we get Ag2SO4. Oxygen dichloride. All right, so oxygen and chlorine are both nonmetals, so we're just going to write it down exactly the way it sounds. So it says we have 1 oxygen. Remember, we don't put the mono on there. And 2 chlorines. We don't do swap and drop. We don't do anything else. We just say, all right, it's just going to be exactly the way it's written down. Another one, it just has nonmetals in it, so we are going to, and it has prefixes. That's actually the best way to tell. If you see a prefix, we're just going to write it down exactly the way it sounds. So we have chlorine, and then it says trifluoride, so ClF3. And then we have nickel 2 hydroxide. So nickel is a metal. So it's got an oxidation number of +2. Hydroxide, that's one of the polyatomic ions. It's OH with a -1 charge. So we swap and drop, and we get that we have 1 nickel and 2 hydroxides. All right, so that is it for the comparison between metallic and covalent bonding, just as far as formula writing goes. So with metallic bonding, that's where you have a metal in a metal. It involves a sea of delocalized electrons surrounding positive metal centers. Properties, metals tend to have mid-range to high melting points. The alkali metals have low melting points, but they're kind of, you don't really get to work with those very much. They are malleable and good conductors of heat and electricity. Covalent bonding, that's where you have just nonmetals, and it involves sharing of the electrons. And for the most part, you're going to satisfy the octet rule. Properties, they tend to be soft solids or liquids with lower melting or boiling points due to that concentration of the electrons between the nuclei. You don't have them delocalized, and they're not transferred. So you kind of have a, lower end of the spectrum. Properties. And you want to use only for covalent bonding. You want to use prefixes to indicate how many you have. And remember, you never ever use prefixes for ionic compounds. So that's going to be anything with either metals or a polyatomic ion present. All right, so that's it for this. Next up, we're going to be looking at drawing Lewis structures and how to determine what the three-dimensional shape of the covalently bonded compound actually is. Thanks for listening.